All right, folks, here we go. Hopefully you get a good look at my beard, not my chin, but here we go. All right, so let's go through this together. Ready? What's an atom? It's got to have protons and electrons that are an equal number, right? An atom is defined as by its protons, but protons and electrons must always be. That's unnecessary, and that's also unfortunate. And we just started this whole thing, and now nothing's working. All right, so protons and electrons must be equal. All right, what's an ion? When protons and electrons are not equal, you either have too many electrons or too few. Because if you change the number of protons, you change the atom. And if an ion is what you're talking about, you're just trying to change the number of electrons, right? Like we form an ionic bond, trading electrons. What's an isotope? It's something where you have two atoms with the same number of protons, but they have different numbers of neutrons. Very good. All right. Now, what's a proton and where is it located? Protons are positive, and you find them in the... I keep waiting on an answer. That's all right. Nucleus. What's an electron and where is it located? Well, it's negative, and you find it in the electron cloud, all right, or the electron orbital. Those terms are often used interchangeably. Now, what is a neutron and where is it located? Well, neutrons have no charge, and you find them in the nucleus. What's an atomic number? That's the atom's number of protons. All right, so the atomic number is just simply the number of protons in an atom. What's the mass number? Well, the mass number requires mass, and for mass, you're going to need to have the only two atomic particles that have mass, which would be protons and neutrons. All right, electrons don't count because they are too, very good, small. Now, how do you identify a random atom? Well, we look at its number of protons. Atoms are determined by their protons, okay? So, if I'm given an atom like this, 1, 2, 3, and with 1, 2, 3, and we'll go with 4. If I'm trying to identify this atom, I count the number of protons. I got 1, 2, 3, and I look at my periodic table, and I see that that is lithium. And so that is my random atom. Now, the next thing says complete the standard. The standard says develop and use models to compare and contrast atoms, ions, and isotopes. So, for all atoms, ions, and isotopes, comparing them, they all want to have the same number of protons. All right, so let's say we're dealing with lithium, for example. Let's go back to that. In lithium, you have 1, 2, 3 protons. And let's say this is my atom. This one's my ion, and this one's my isotope. All of them must have 3 protons. Otherwise, it will no longer be lithium. Now what I want to do is find the number of electrons for an atom. How many electrons? 3. They got to equal the number of protons, right? 1, 2, and 3. We'll just put them around there like that. Now, when we get our atom, we also need to have 1, 2, 3, I think 4. 1, 2, 3, 4 neutrons there too. But anyways, for our ion, we're going to have how many electrons? 2 or 4. It just has to be different than 3. If I got 3 protons and 3 electrons, they balance out. So for ions, I can just use 2. Because then I have a positive 1 ion. I got 3 protons and 2 electrons. Or I can do 1, 2, 3, 4. And that will give me 4 electrons and 3 protons with a negative 1 charge. That will be an ion. Ions are always either positive or negative. And then modeling my isotope, well, if lithium is supposed to have 4 neutrons, then the isotope can simply have 2, or none, or 1. Isotopes differ in the number of their neutrons. Okay? Any questions there? All right, moving on. Analyze and interpret data to determine trends of the following: valence electrons, ions, metals, nonmetals, and phases. So the whole reason I wrote these out all the way like this was so you could see the pattern here in these and how they go. I think this is the first 20 atoms or so. So, starting with these. Hydrogen, how many valence electrons? 1. Helium?
8.
No. The first shell only has 2. All right? And then after that, we go to 8. So, if you would, first shell only has 2 atoms in it. And so, or should be 2 electrons in it. If you would, lithium? 1. Beryllium?
2.
Next?
3. 4.
5, 6, 7, and 8. And I get all the way to neon. That gets me all the way to the right side. And neon just happens to be a noble gas. It does not interact because it has a full set of outer shell electrons. How many is in a full set? 8. So that means we have to start a whole new electron orbital or shell. So sodium is 1, then 2, then 3, then 4, then 5, then 6. Bring it on down. We got 7, then 8. All right, and we're all the way back to argon, which has 8. So again, we have another noble gas. Do they react? No, they don't, because they have 8 valence electrons, and so therefore they do not need to gain any more. Now, what ions do they form? Well, if we're looking right here, I really want you to pay close attention to this because this is the crux of it. Valence electron-wise, everybody wants to have how many? 8, right? Or 2, right? Or 0. But let's just say 8 for right now, right? So what's easier for hydrogen to do? Is it easier for it to gain an electron or lose an electron? Either or, actually. Hydrogen can do both because it can only have how many electrons in that shell? 2, right? So it will form a positive or a negative ion, depending upon what the situation is. But it's usually a positive ion. Now, what will helium do? It'll do nothing because it's got the maximum it can in that shell, right? 2 valence electrons, so he's happy. Now, what about lithium? That's going to give up this electron. It's easier to give up this 1 extra electron and become stable like helium as opposed to gaining 7 new ones. That's a lot of energy, a lot of time. So it's easier to give that 1 up to be happy. What about beryllium? Plus 2. It's giving up those 2 electrons. Boron? Positive 3. Carbon? Yeah, because look, it can gain 4 electrons or lose 4 electrons, whatever's the easiest here. So it's just going to be right there in the middle. Either or. What about nitrogen? Now, why a minus 3, though? Because it's gaining what? Negative electrons, right? And they're all negative. So therefore they gain a negative 3 charge. Oxygen needs to gain 2 more, because 6 plus 2 is 8. So it gains a negative 2 charge. Fluorine's a negative 1, and then neon is a 0. And that's the pattern of our oxidation numbers. Okay, and why they happen like that. All right, and it'll continue on down here with sodium through argon. All right? If you would, metals, nonmetals, or metalloids. Hydrogen. Non-metal. Helium. Non-metal. Lithium. Metal. Beryllium. Boron. Metalloid. All right. Nitrogen, or excuse me, carbon. Non-metal. Nitrogen. Non-metal. Oxygen. Non-metal. Fluorine. Non-metal. And neon. Non-metals. So again, we're moving from metals to non-metals, and depending upon where we are in the periodic table. So this would be our first shell. This would be our second shell. So we move in each shell from metals to non-metals, depending upon where they are in the periodic table. How about phase-wise? What phase or what state of matter is hydrogen in? It's a gas. What about helium? A gas as well, right? So non-metals are mainly gases, right? What are metals going to be? Solids. What about what about metalloids? Solids as well. And carbon is one of the few that are non-metals that's actually a solid, like wood, right? Or diamonds. That's carbon as well. So nitrogen and the rest of these are all going to be gases. Okay? Non-metals are gases except for a couple of them. Most non-metals are gases. What's the only 2 liquids on the entire periodic table? Mercury and bromine, right? Other than that, they're either going to be metals and solids or non-metals and likely gases, okay? And the rest of this you can fill in the same because I think you guys know what we're doing there. So what are valence electrons? The number of electrons in the outermost shell. What are oxidation numbers? What is it?
Number of valence electrons.
No, that's the valence electrons. What's oxidation number? Look at these. When we list the oxidation numbers, what do we see here? Gaining and losing electrons, which makes you an ion. Exactly. Oxidation numbers are the ions that they form. Does that make sense? So lithium will lose that 1 electron, and if it loses an electron, it becomes +1. That's an oxidation number, all right, when it forms an ion. All right, so down here, oxidation numbers are the ions that they form when they bond. What do I need to know about metals? They conduct electricity, they're shiny, and they're bendable. The word is malleable, all right, malleable. All right, and anyways, moving on through here. What do I know about nonmetals? They're not shiny, they're dull, right? They don't conduct electricity, and they're breakable, right? We call it brittle. You can break them, right? I can break a piece of wood, right? Right? It breaks. It doesn't bend. At least not that much. And then metalloids are kind of in between, right? They're semiconductive, all right? Some are hard, some are brittle, you know what I mean? Some are bendable. It just depends. They're kind of the in-between place. What's a group?
It's a family.
It's like a family, but it's a column of atoms in the periodic table, right? And then the family is essentially the same thing, except in the family, these column atoms share the same traits, exactly. And usually because they have the same number of valence electrons, right? Which we write the Roman numerals there for. Okay, so use the periodic table to predict the above properties for main group elements. And I think that is gone. However, if we're writing things here, it's weird. What are my valence electrons going to be? How do they represent them in the periodic table? With the Roman numerals, right? Or Roman noodles here. So, if you're looking through, you should see all these in the periodic tables that you guys have been given. All right, it'll actually show you that, I believe, if you look at the top. So when you're given these, look across the top, it says 1A, 2A, 3A, 4A, 5A. Just ignore the A's there and look at the Roman numerals to figure those out, right? And then oxidation numbers, plus 1, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1, and 0. And everything in that column operates the same way and has the exact same oxidation number. Okay? Let me see. Where are my metals? Metals are on the left, not hydrogen, all the way through here. And then we have our metalloids here in the middle, right? Along the stair-step ladder. And what are these guys over here? Those are my nonmetals. So these will be my solids and conductive, right? These will be my gases, except for carbon and a couple others. And they will be non-conductive insulators, okay? And then your metalloids in the middle. All right, rolling it on down. Analyze and interpret data to predict properties of ionic and covalent compounds. Write the properties here. What are the properties of ionic bonds?
High melting point.
High melting points.
And highly conductive.
And conductive, good. High melting points, conductive, and high boiling points, I believe is the other thing, right? All right, and they're also made up of a metal and a non-metal. All right, let me see, covalent bonds. Two non-metals. Low melting point and boiling point. Do they conduct? Not conductive. All right, and then what kind of bonds do they have? Weak or strong? Weak. All right, that's why they mainly form what state? Liquids or gases. All right, ionic bonds are strong, and so they will form solids. All right, and that should all be straight from the song, correct? All right. Develop and use models to predict formulae for stable binary ionic compounds based on balance of charges. Develop models and name Mg plus Cl, Li plus N using oxidation numbers only. So if I'm bonding Mg and Cl, right, and I'm bonding Li and N, right, I need to use oxidation numbers only. What's the oxidation number for magnesium? 2 is not an oxidation number. Positive 2. Chlorine? Negative 1. And what do we do with these two? Swaps the doodle, right? And we get MgCl2. We good with that? What about lithium and nitrogen? Plus 1 and minus 3. And we switch and we get Li3N. Yep. Swaps the doodle. Li3N. Okay? Bring this on down. Naming ionic bonds. Number 1, what do we name this guy? Magnesium oxide. Number 2, lithium sulfide. Number 3, calcium fluoride. Number 4, Potassium nitride, number 5.
Sodium chloride.
Sodium chloride, back over here to covalent. Number 1.
Dinitride trioxide.
Dinitrogen trioxide. Now we have to use our prefixes, right? Ionic does not, covalent always uses prefixes. Number 2.
Dihydrogen monosulfide.
Dihydrogen monosulfide. Only use the mono second. 3. Diboron pentaoxide. Then you got mononitrogen trihydride, right? No, because we only use the mono second. So we have nitrogen trihydride, and then octocarbon decahydride. Just because. All right. Anyways, over here, naming these. So this time we're going to change it to the formula. Okay. And again, looking at these, you can tell which ones are ionic, right? Which ones are ionic? 1 through 4, right? So, sodium oxide, NaO would be incorrect. Na2O. So this is where you gotta be careful. When you're making the formula here from this with ionic bonds, the reason they don't give you the actual prefixes is because all you gotta do is use these numbers. All right, and then you do what? The swaps and doodle there, right? So barium plus 2, chlorine minus 1. So what would this be?
Basic 2.
Barium, Ba, and Cl2. Yes. All right. Aluminum oxide. Al2O3, because oxygen is minus 2, aluminum is plus 3. You kind of see how that works? Yes? All right, and then lithium oxide, plus 1, or lithium iodide, I should say, minus 1, and we get Li. Yeah? Okay, cool. Iodine pentafluoride,
IF5.
IF5. Dinitrogen trioxide, N2O3. Carbon monoxide,
CO2.
carbon monoxide, CO. That's carbon dioxide. All right? And then phosphorus triiodide, Pi3. Yes. So you cool with that? That's why it's weird with ionic bonds, but they get away with no prefixes because you should know the oxidation numbers. All right? You should hopefully be familiar enough with them to get most of them by heart right now. But if not, that's okay. That's what the periodic table is for. Now, plan and carry out investigations to demonstrate the conservation of mass. All right? So in any experiment for conservation of mass, what's the general outline? What do I have to do? Measure the mass when? Before and after. That's straightforward, right? All right. Now, what would you have to be careful about with gases? Keep them in a closed container so they don't escape, right? All right. So give examples of synthesis, decomp, and replacement reactions. So synthesis reaction. A plus B equals AB, or C. Well, I guess you say C. Well, you can do AB. That's a much smarter thing to put. Very good. All right, so decomposition. AB becomes A plus B. They decompose. They separate, right? All right. Single replacement. A plus BC will give me AB plus C. So we only swap one thing out, right? You're swapping the A and the C. Just one thing there. Does that kind of make sense? So it's a single replacement. What makes a double replacement?
2 switches.
Yeah, you got 2 compounds here, right? And you got 2 switches. You're going to swap the A and the C, and then you're going to swap the B and the D. So we have 4 total things here swapping around, right? So we get BC plus AD. All right? Okay. Now, moving this on down. Balance and give reaction type. So we balance this equation out. P4 plus O2 gives you P2O3. Anytime I got an odd number, I want to make sure I do what?
Multiply
By
2.
2. Because if I got odd numbers over here and I got even numbers over here, doubling that odd will make it easier to balance, right? So I would start by putting a 2 here. So now let's figure it out. How many P's do I have?
4,
And O's?
2,
2. And then over here, P's, 4, O's, 6. Now, are the P's good? Yep, they are. And what about the O's? Nope. So we're going to raise this side up, right? By doing what?
3 times 3.
Putting a 3 right here. So 3 times 2 is 6. And we get P4 and O6. And the coefficients there are 1, 3, and 2. Is that good enough? Yeah? All right. What about this next one down here? We got coefficients for that? What you got?
I got 1 CF4 and 2 BR2 and 1 CBR4 and 2 F2.
Looks good to me. 1, 2, 1, 2. Is everybody good with that? Want me to go over it? All right. What about the next one?
1, 1, 1.
1, 1, 1. Is that right?
It should be.
Are they all ones?
That's what I got.
I have 1 barium, 1 barium, 1 sulfur, 1 sulfur, 1 platinum, 1 platinum, 2 fluorines, 2 fluorines. Yep, that's 100% balanced already. Very, very good. And the next one?
6, 9, 3.
6, 9, 3. Now, 6, 9, and 3 are 3 numbers that share a common factor of 3. So when you get 6, 9, 3, that should tell you, uh-oh, I've done too much. Okay? So you see this is all 1s and it's balanced? It could also be all 2s and it would still be balanced. You want to have the most reduced form of the equation. So it's not 6, 9, 3, 2, 3, 1. Divide them all by 3 because they share a common factor of 3, right? Now here's how you keep that from happening. So look right here. So here's what I would do if I were you. So when I see this already, I see evens on one side and an odd on the other. What did I say to do in that situation? Put a 2 here. Don't even do anything else. Just go ahead and put a 2 there. And that gives us 2 nitrogens and 6 fluorines. And then over here we've got 2 nitrogens and 2 fluorines. So what do we do here?
Times 3 on F.
Put a 3 there. And then that's the balanced equation. Right? So we get 2 blank 3. Or I guess you got 6, 3, 9. Maybe when you did this the first time. But either way, that's what it should be right there. And does that make sense? And I'll get the 6. So we have, again, even numbers of mass on both sides. Okay? All right. Develop a model to illustrate fission and fusion. What's fission doing? It's taking what chemical? What element? Uranium, and turning it into? What 2 things did we say? Kr, krypton, and Ba, barium, right? And now how does it split? Because uranium there is not going to split on command. So how do they make it split?
They add a neutron.
Yeah, they add a neutron. So we see a neutron coming in, making it split. It makes these 2 things and 3 what?
Electron.
Not electrons. Neutrons. We're dealing with nuclear things, right? What's the key word in nuclear?
Neutron.
Nucleus. Right? And where are electrons? They're around the nucleus, right? So we're dealing with the nucleus. We're only dealing with protons and neutrons. So electrons don't come into it really right now. Okay? Except with beta decay. But fusion, what would fusion be? 2 things coming together, right? What 2 things though?
Hydrogen and
Hydrogen 2, better known as deuterium, right? And tritium. So hydrogen with 2 neutrons. All right, deuterium, 1 neutron, and tritium, 2 neutrons. Still hydrogen. They come together to form what? This little 5-particle thing, that's basically helium, right? A helium-5. So helium with a mass number of 5. Protons plus neutrons is a mass number. Okay? And then that's a little unstable, so it breaks apart into a helium nucleus and a single neutron. Okay? So this is fusion, using hydrogen to form helium. Are we good with that? Alrighty. Keep track of your protons and neutrons to identify waste products. You'll see that on the study guide from the Georgia State Department. Okay. We need to count our numbers of neutrons and protons and waste products. Matter must always be conserved. What's an alpha particle made of?
2 protons, 2 neutrons.
2 protons, 2 neutrons. What stops it?
Paper.
Paper. A beta particle, what's it made of?
1 electron.
1 electron. What stops it?
Aluminum.
Aluminum does. What's a gamma wave? Or gamma ray?
Energy wave.
An energy wave. It's just energy, right? What stops it?
Lead.
Yeah, technically nothing, but lead will do the best thing it can, right? Or best that it can. All right, so looking at half-life. A couple things to keep in mind. Now, half-life is a time, right? The amount of time for what to happen?
Decay.
Half to decay, right? Now, it's never quite perfect, but it's always pretty close. So this point right here, right, would be considered the halfway point, right? And that's, therefore, where the half-life comes in. So looking at this right here, what would the half-life be of uranium-235?
750 million years.
Yeah, so right here, it's just below 1 billion years, right? About 3/4 of the way across. You're looking at your x-axis here, right? So it's not quite 1 billion years. So you could say 750 million years. I believe this was a quiz question on one of them before we did, right? But if I want to know the time, all I got to do is look at the length of time it took to be reduced by half. Does that make sense? So if it's 750 million years, then 2 of those would be 1.5. And if we look at 25% left, it's about 1.5 years. Okay? So half-life is the amount of time it takes to be reduced by half. All right? And we use it to tell how old things are, right? Such as the Earth or bones and fossils that we find. Okay? What's the half-life of uranium-235? We said 750 million years, so 0.75 billion or so. From the graph, how much uranium-235 is left after 3 half-lives? How much is left after 3 half-lives?
15%.
How much?
15%.
15%? So we got 1, 2, 3. 15 is close. I think 15 is a good number. But the honest answer is, if it goes 50, 25, what would the third one have to be? 12.5. So that's where 15 is pretty close. It looks about that. Okay? But 12.5 is a little more technically accurate, or I guess predictive than it is accurate. But okay, is everyone good with that? All right, moving this forward. How does half-life work with percents? Well, you always start out with what percent? With percents. Always start out with 100%. Exactly. And then you move from there, right? What about with fractions? What number do you start with?
1.
With 1. All right. Otherwise, you just use the grams. Okay, so let's look at those problems. If there are 60 grams of hydrogen mononitride, and it has a half-life of 20 years, how much will HN remain after 100 years have passed? So what do we do first? Starting amount was 60, and then reduce it by half. How long does that take? 20 years, right? I got to keep doing this until I get to what number? 100, right? So 60 becomes 30, then 15, and that took another 20 years. That's 40. And again, 7.5, that's another. And then again, 3.25. Yeah. Oh no, you're right. 7.5. Yeah. 3.75. All right, that's another 20 years. So let me see. Oh, I'm doing this wrong. You got to make sure you draw your lines next to the old arrows here. So that's 20, and that's 20. So we've gone through a total of 80. We got to do one more, which gives me 1.875, something like that. You have a calculator? 1.875, and that's a total of 5/20s, which is 100 years, the total time. Are we good with that? All right, so if there are 120 grams at the start and 15 grams left now, how long has it been decaying? So you go from 120 all the way down to what? 15. So that would be 120 would be 60, and then 30, and then 15. Oh, that's not many. So how many half-lives there? 1, 2, 3. And each half-life is 20 years. So what's the total time here? 60. Are y'all good with that? Okay, moving it down. Fission and fusion. All right, applications for fusion. We want to use it for power, right? But can we? Can we use fusion yet? Why not? Too powerful. We haven't figured it out quite yet, right? Now, what about applications of fission? We use it to make lots of energy, electricity, right? All right, so we use it to make electricity here. The benefits. What would the benefits be if we could do fusion? Lots of energy and zero waste, right? No waste. Because, again, the only thing made is what? Helium. They hydrogen make helium. That's pretty great. What are the problems? We can't do what? Can't control it yet, yeah? Okay, how about the benefits of fission? The main thing. Why do we do nuclear power at all, as opposed to just using coal?
The waste, there's no chemical, right?
Yeah, well, chemical waste, what kind of waste? What is it that coal and natural gas produce that we don't want?
Smoke.
Better known as?
Fossil fuels.
Which make?
Fire.
You have to know this.
CO2.
Carbon dioxide, right? Carbon emissions. You cannot release carbon dioxide in the atmosphere because it increases climate change, right? Global warming. There are some storms raging in the Antarctic right now. In fact, the second largest colony of emperor penguins is being destroyed because of storms breaking the ice where they lay their eggs and hatch their eggs. And so they're being wiped out year after year. Because we have too many storms down there because the weather's crazy because of global warming and climate change. But anyways, benefits. No CO2 released, at least directly, okay? And then over here for problems, the waste products, right? But what do we do with it just in case? Put it underground, okay? Either way, this is, again, an improvement over fossil fuels, all right? The problem is we just got to make sure we're taking careful control of it because if there's a meltdown, it can destroy the area that it's in, right? Like Chernobyl did. All right, moving this forward. Asking questions to compare and contrast models depicting particle arrangements of a solid. So, model a solid, what does it look like? Nice, neat, orderly what? Rows. Liquids. Mixed and matched around, right? The gases are spread out, right? Now, shape, volume, and density of each. Here's the deal. For a solid, liquid, and a gas, in terms of shape, the solid keeps its shape, right? We call it a definite shape, all right? For a liquid, it has an indefinite shape. It loses its shape, right? And same thing for a gas. They all have an indefinite shape. Volume-wise, solid always keeps its volume, right? The liquid always keeps its volume. No matter how much you want to squeeze that bottle of Coke, it's not really going to change its size, right? The volume pretty much stays the same. Gases, however, their volume, as soon as you open the container, what do? They go flying everywhere, right? So they have an indefinite volume. And which of these is the most dense? Solid, less dense? Least dense, I should say, is gas. And then liquid's right in the middle. Okay? All right. Asking questions. What questions can we ask about solids, liquids, and gases? Keep it to characteristics. We can ask which one is more orderly, right? We can ask how much energy does it take to move from one to the other. We can ask does heating affect a gas? Does heating affect a gas?
Yes.
Yeah, because it turns into a what? A plasma. And what do plasmas have? Positive and negative particles, right? All right, so I think we're good there with those questions. Those questions you can practice up on our quizzes, right? Okay, now looking at this. Plan and carry out investigations to identify relationships among temperature, pressure, volume, and density of gases in a closed system. What is density?
It is
Density is how closely packed the particles are. So look at this first one. Is this more or less dense? More dense in this one, right? More particles in that same area. So density is how tightly packed the particles are. Okay? Now, draw constant, direct, and inverse graphs. So if you have a graph and it's moving like this, what would you call it? Constant, direct, or inverse?
constant.
That's constant. If I have a graph and it goes up like this, what would I call it? Direct or inverse? Direct. When one increases on the x, the other increases on the y. You with me on that? And then over here, what would an inverse graph look like? Inverse means opposite. So when one increases, the other decreases. We call it a negative slope. All right? Now sometimes they'll show it like this with a little bit of a curve. But either way, inverses, right? It should show it going down, right? For example, this is kind of what solubility is, right? And solubility, as temperature increases, solubility increases, right? But for gases, as temperature increases, solubility decreases. That's an inverse relationship. You see what I'm saying? One goes up, the other goes down. So in inverse, they're just opposites of each other. All right, what properties of gases have a direct relationship? Both work together. Volume and temperature, and pressure and temperature. All right, what should you use to answer these questions?
PTV strip.
PTV strip, right? On your PTV strip, if you hold pressure constant and increase temperature, volume goes up. All right? If you hold volume constant and increase pressure, temperature goes up. They have a direct relationship. Which properties have an inverse relationship? Opposites. When one goes up, the other goes down. That would be which ones?
T and P. Oh, wait. Oh, P and B.
Yeah. If you hold temperature constant, increase volume, pressure goes down. That's why they're on opposite sides from each other, right? So when you make a PTV strip like this, volume goes up, pressure goes down. They have an inverse relationship. We cool with that? All right? Now, what does it mean for a property to be kept constant? It means you don't change it, right? You don't increase temperature, you don't increase pressure, everything stays the same. All right? Draw a syringe. So, if you don't know what a syringe is, it's this little thing with a little nozzle that we had earlier this year, right? And it's got a little plunger at the back. And to increase pressure on it, what do? Squeeze it, right? Yeah, right? You squeeze it a little bit. And so anyway, squeezing it will increase the pressure and therefore decrease the volume because they're opposites, right? Inverse. Increase pressure, decrease volume. Okay, moving this on down. What is conductivity? The ability to conduct electricity. How do you increase conductivity in the solution? We want to get more ions, right? Ions in solution. All right, so what is conductivity? Ability to conduct electricity. You want to increase the number of ions in the solution. Why is distilled water not an issue during electrocution?
Because there's no ions.
There are no ions, exactly. So no ions, no conducting of electricity. Make sense? All right. Draw a model of solute and solvent making a solution. Solute, solvent equals solution. Mixed together. Is that easy enough? Yeah? Solute plus solvent gives you solution. The solute is a smaller word, solvent is a bigger word, and therefore the solute always goes into the solvent. Okay? All right. Draw a model showing how salt or an acid and base can increase conductivity in a solution. Well, if I add a salt, right, that's going to release, it's an ionic bond, so it's going to release lots of positives and negatives, and will conduct electricity, right? If I add an acid or a base, an acid will add lots of H pluses, right? And there would be an opposite part that would be a minus there. So again, you're getting lots of ions, which conducts electricity, right? So acids have H plus. What do bases have? OH minus. Again, that's an ion, right? So it conducts electricity. So acids and bases conduct electricity too. Okay? Let's see. Model concentrated versus dilute. So if it's concentrated, what should I see? A lot. And if it's dilute? Not that much. Dilute. Concentrated. We good with that? All right, rolling it down on here. plan and carry out investigations into temperature, surface area, and agitation. So, let's talk about this. To increase the solubility of a solid, what do I want to do to temperature? To make that good Kool-Aid, what do I do? Increase temperature, right? So I can fit more what in there? Solute, yeah. Sugar in this case, right? For Kool-Aid. So, increase temperature for a solid. What do I do to a gas? Decrease temperature, right? So I've been drinking this Coke here for a while, right? It's gotten warmer. So guess what there's less of in here now? Carbon dioxide. Yeah, carbonation. All that carbon dioxide is leaving.
You're just making me want a soda.
You can have one.
I know where it's going.
All right, surface area. For a solid, what do I want to do? Increase it or decrease it? Increase the surface area. Because if I have more surface area, right? More surface is exposed to the water, and the more the water can pull it apart. Are we good with that? For gases, the surface area doesn't matter. You with me on that? What about agitation? What does agitation mean?
Stirring.
Stirring, right? So, do I want more or less stirring for a solid? More stirring, right? Now, do I want stirring for my gas? What happens if you shake up your can of soda? Yeah, it kind of leaves, right? Now, what I do want, however, I don't think I put on here is to get the gas in, I don't want to increase surface area, but I do want to increase what?
Pressure.
I want to increase pressure, okay? You see question number 42, scratch that one out. I'm going to have to edit this. I don't like that question anymore. Variables and constants. Variables change and constants stay the same. That's all it really talks about, okay? But I don't really want you to worry about that. All right, so design an investigation of how surface area affects solubility. All I need to do is take something and do what? Crush it up, okay? So if I'm designing an investigation, I have one thing where I keep like a cube, like a sugar cube, right? And the other one, I take the sugar cube and I do what? Crush it up and compare to see which one will dissolve faster. Does that kind of make sense? So sugar cube experiment versus granular sugar. We did that in class too, didn't we? All right, how do I design an investigation of how agitation affects solubility? Same thing. I take one, right, which I'm going to put as my control, where I don't stir, and another one where I do stir. Does that kind of make sense? Yes? All right. Why aren't liquids involved in the table above? Well, because they just already do what? They already mix. All you gotta do is stir them around, right? So that's not too bad. Okay. Let me see here. What is supersaturated and how do you make it?
Heat it up.
You heat it up, right? Supersaturated means it's got more than it should, right? It's got so much in it that if you add an extra crystal, what does it do? It crystallizes out of solution, right? What is saturated?
The
Highest amount you can put in there, right? So how do you make it? Well, you just mix stuff in until no more dissolves, right? And it starts falling to the bottom. All right. What is unsaturated? Means I can put more in there, right? So that means I've stirred some in there and there's still room for more. So I can still add more in there, right? How does temperature affect the solubility of a solid? Well, increased temperature, increased solubility. How does temperature affect the solubility of a gas? Increased temperature, decreased solubility, right? Draw what a gas would look like on this graph. What's the solubility of KNO3 at 80 degrees? Well, I go to 80 and then I go up, and that's about what number? 170? 160? Somewhere in that range? Yeah? All right. Describe the solution as saturated, unsaturated, or supersaturated at 200 grams at 40 degrees. So right here. 40 degrees, 200 grams. Is that saturated, supersaturated, or unsaturated? Supersaturated. All right. Obtain and communicate information about the relationship between structure and properties and pH change in acids and bases. For an acid, I'm going to have what particular ion?
H+.
H plus. All right. For bases? OH minus. All right. How do the acids taste?
Lemon juice.
Sour. Lemon juice, sour. What about the bases? Bitter, right? So we have sour, we have bitter. All right? Let me see. Structure and properties. All right, pH of acids.
Red.
pH.
Oh, pH.
0. Yeah, well, let's just say 6.9. Okay? And then for bases? 7.1 through 14. Okay, the whole pH scale goes from 0 to 14. All right? What's right in the middle at 7? Neutral. That would be just water, right? Okay, now, acids turn litmus paper what?
Red.
Yes, so it turns litmus red. All right, and bases turn litmus blue. So this is weird, but what color litmus paper do I use to determine if it's an acid? I want to use blue because it will turn it red. And I want to use red for a base because it will turn it blue. Okay? All right. Draw a pH scale and highlight strong and weak acids and bases. On the pH scale, from 0 to 14 and 7 being neutral, where are the strong acids? On the left over here are strong. Where are the strong bases? Over towards 14. And which ones are weak? The ones that are around 7, right? 6 and 8. Okay? How can I tell if something's an acid or a base? I can taste it or I can use pH paper, right? What are some common acids? Lemon juice. You're still salty about that. Yeah, I know, I got you. Vinegar. Coca-Cola. Fruit juices. Right? Milk, even. What are some common bases? What?
Dark chocolate bitter.
Dark chocolate? Oh, interesting. I hadn't thought about that. What'd you say?
Drain
Chlorine? Or Clorox? Drain cleaner. Is that what you said? I'm sorry. Yeah, so any cleaning products. Cleaning products are bases. Antacids, right? Don't forget antacids means anti-acid, right? So that helps for that. Egg whites, baking soda, okay? Drain cleaner, Clorox, bleach, all that stuff. Okay, yeah, don't drink drain cleaner, exactly. All right, let me see. Standard 7, we got energy transformations. So looking at these, give examples of each. What are the examples of chemical? Batteries. What else? Stomach.
You're pointing at your stomach.
Yeah, why?
Stomach acid?
No. We talk about this all the time. We play our little game. Why you put your hands here? Your fat. Anything using your body, it's the storage of fat, okay? All right, or food that you eat, right? Storage of fat and food. So your stomach has something to do with it, right? Digesting food, okay? But your intestines will soak it up. But so you got batteries, food, and what else? And gasoline, right? Batteries, food, gasoline, wood, that kind of thing is chemical energy. Mechanical energy. Yeah, movement, right? Anything moving. It's also known as kinetic, right? Electromagnetic. That's light, the EM spectrum, right? So you're talking visible light, X-rays, gamma rays, all those things. Microwaves, okay? Infrared. Sound. Just a sound. Yeah, I mean, it's simple enough. Thermal. Anything hot or anything cold, okay? Electric. Anything plugged into a wall, right? A flashlight. Now, a flashlight uses chemical energy, but it changes. The battery is part of chemical, or excuse me, it's part of chemical, but it also creates electricity, right?
Lamp.
So, well, a lamp would work, yes. But for electric, you could say a flashlight, but it starts out with chemical and then goes to. So for a flashlight, it will start out with chemical and then go to what? Then it's electrical, and then it's to light. You see what I'm saying? Okay? So again, chemicals involved, electricals involved, but just one follows the other. Okay? Nuclear.
Explosion.
Explosions, but yeah, uranium, right? Fission and fusion. So uranium and the sun. Nuclear fusion and nuclear fission. Now, where does most energy disappear to? Energy can't be created or destroyed. It can only be changed. Where does most of the lost energy go? On our roller coasters and stuff, for example. Where did a lot of that energy go from potential and kinetic? Heat. When the marble rolls along the track, right, it creates lots of friction, which makes lots of heat and gets lost that way. So does the energy actually disappear? No, it's just changing the heat. Okay? Explain the transformations in a rock concert. What's the transformations in a rock concert?
The speakers.
Speakers changes.
They plug into a wall, right?
Yep.
So they plug into a wall that's
electrical, and it makes
sound.
Sound,
and
right?
It hurts your eardrums.
Yeah. I mean, you can even go this far. You could say it starts with chemical because they're playing guitar, right? And it's changing that, right, into vibrations, which would be sound, which is then converted into electricity, which goes to the speaker, which is then converted back into sound, right? This is a chemical, kinetic, sound, electrical. I mean, it depends on how technical you want to get. You just got to think through the process, right? Flashlight, we just did that. Chemical, electrical, and light. And all things that make light also produce heat, correct? So you could say heat as well. Shooting a basketball. I'm doing it, so it starts with what? Starts with chemical. I can't do anything unless I did what earlier? I ate. Exactly. I can't do anything without food. That's why people die when they starve, right? So I need energy. So before I can shoot a basketball, I have energy, stored chemical energy, and then I convert that into what? Kinetic energy, and I shoot the basketball in the air. Gravitational. Exactly. All right. Roller coaster. Start out with it high or low? High for lots of what kind of energy? Potential energy, gravitational potential, right? And it converts into? Well, gravitational is potential. When you say potential energy, you mean gravitational. Okay? It's called gravitational potential energy. Okay? So gravitational potential energy gets converted into? Kinetic. Right? And maybe a little bit of heat too. Okay. And sound, I guess. Now, plan and carry out investigations to describe the molecular motion in thermal energy changes. So how would I study conduction? Conduction needs things to do what? Touch. Well, let's talk heat a bit. Kid, honestly, I can go on and on. I can explain hot natural phenomenon, a pot, a spoon, a sound. With conduction, you...
Touch and go out.
So I need things to touch, but what typical things to touch? Solids, right? It primarily happens in solids, all right? So if I want it to be just conduction, solids is the name of the game. Liquids and gases can touch things too, though, right? But for the most part, you're going to be talking about solids with conduction. What about convection?
No touching.
Convection currents in liquids and gases. It doesn't happen in solids. Why not?
Because they can't move around as much.
Because they can't move. Yeah, exactly. They're stuck in place, right? So liquids and gases, hot things go up because they're less dense. That's the whole idea. Hot things go up and cold things will crash. How do I study radiation? Any investigation of radiation is always concerned about this one thing.
Radiation wasting.
It has to do with light, yeah. So since it has to do with light, it has to do with a vacuum. If you see anything to do with a vacuum, it means you no longer have a solid, liquid, or a gas, right? So therefore, it can't be convection, it can't be conduction, it can only be radiation, okay? And we're talking about infrared light here, okay? So draw a model of all three. Well, you should know that conduction is when the particles are all bouncing into each other, right? And moving the heat along sideways, okay? You know that for convection, hot things go up and cold things go down, right? And for radiation, let's say like a light bulb, for example. That's not a light bulb. It's kind of a light bulb. All right? So for a light bulb like this, right, radiation sends light in all directions, okay, through a vacuum, all right, or through gas as well, but in all directions. Okay, what's specific heat? The amount of energy required to raise the temperature 1 degree of matter, okay? So, for good conduction, I want what kind of a specific heat? Do I want high or low? I want low specific heat. Specific heat is the amount of energy required to raise the temperature 1 degree, right? So a conductor should change temperature really quickly, which means it must have a very low specific heat. I want a low specific heat because I want it to increase the temperature or decrease the temperature quickly. Does that make sense? Yes? Now, for an insulation, I want a high specific heat because I want it to take a long time to change temperature. Does that make sense? Yes? Low specific heat will quickly change temperature. All right? Come in. And then the high specific heat will take a long time to change. I'm actually recording something. If you can give me about 3 to 5 minutes, you can stay back there. That's fine. All right, you with me on this? Yes? All right, moving this forward. What's the equation that uses specific heat?
Q and K.
Q equals MK, right? What does each variable represent? What's the Q? That's the heat gained or lost, right? That's the thermal energy, okay? What's the M? Mass. What's the C? Specific heat. And the delta T? The change in temperature. The final minus the initial. Okay? What does each variable represent? We did that. Include the units. So the units for Q is joules. The units for mass is grams. The units for specific heat is that weird one. Joules divided by grams times degrees C. And then you got temperature, which is degrees C, or Kelvin. Okay? And if you don't have time to write it down right now, ladies, don't worry too much about it, okay? It'll be put up later, okay? Now, doing the math work here, how much heat is lost when 50 grams of water with a specific heat of 4.184 changes temperature from 32 to 14 degrees. That number's wrong. But how do we find that? Well, how much heat is lost, that's the Q, right? Is mass times specific heat, 4.184, times the change in temperature. What's the change in temperature? 32 minus 14? What does that give us?
18.
18? Now, it went from 32 to 14, right? Final minus initial. So you put 14 minus 32. And what do you get there?
Negative.
A negative 18, because you're losing temperature, right? So, times, that is, yeah, times a negative 18 equals, well, it should be a negative one of these. A negative 4,332.6 grams. Are we good with that? All right? So remember, it says how much heat is lost. That means that you're getting cold. Does that make sense? So it'll be a negative number. Okay, explain the flow of energy in this. We know from A to B, that's a solid. Yeah. From B to C, it's changing into a liquid. From C to D, that's a liquid. And from B to E, change to a gas. And then from E to F, that's the gas. So remember, it flattens out every time the energy is being used to change state instead of changing the temperature. Okay? And that's where you see that flattening out. So it flattens out at 0 places because they're changing state from B to C and from D to E. Okay? In what 2 ways can I change something's state? Well, I can either increase or decrease pressure, or I can increase and decrease the temperature. All right? Remember we boiled water at like 50 degrees? I had that syringe, right? And I got 50 degree water in there, and then I decreased the pressure. So with 50 degree water, that's right here, and I decreased the pressure, it became water vapor and started boiling. Okay? All right. Now, I don't know if we have too much time to go through the rest of these, but I'll answer what I can as quickly as I can. The equation for velocity is distance divided by time. The equation for acceleration, delta V over delta T, right? Okay. How do I calculate velocity? I need distance divided by time. For acceleration, I need velocity divided by time. How do I know if something's moving? What has to change? The distance has to change, right? If I have a distance that's constant, it means the object's doing what here? Not moving. It means it's staying the same because this distance stays the same. Does that make sense? All right. And if I see the distance increasing from 10 to 30 there, that means it must be moving, right? How do I know if something's accelerating? The only way to know if it's accelerating is if velocity is doing what? Increasing or decreasing. So from A to B, is it accelerating? Yeah, positive acceleration, right? From B to C, velocity stays at 4, so it's not accelerating. We have an acceleration of 0. Positive acceleration, 0 acceleration, and from C to D, a negative. Because the velocity is going down, therefore it's slowing down, a negative acceleration. We good with that? All right, rolling it on down. How can you use the graph on the left to calculate velocity? Well, we'll work on that a little bit later. Okay? So, the rest of the study guide, I feel like you guys should be able to handle on your own. Good luck. All right? And, well, good luck.